like the wild feeding frenzy where you get to use your elbows, or do you prefer the more organized way that I'm doing it? Okay. That's what I thought. But, you know, you never know sometimes. Okay, so the high score in the exam was 100%, believe it or not. And there's some people in the 90s. The low score was too low. But the good news, at least for a reasonable part of the class, is that people are starting to figure out how to solve problems, not just write down wild guesses on a piece of paper. So even though I see, a few too many pentavalent carbon atoms at this stage, still there are people who are, trying to who've learned the technique of at least methodically going about solving the problem. Regardless of whether you end up with the right solution or not, that's the first step. Now, having said that, there's still, a fair number of people in the class who are, lacking some fundamentals. As is often the case, sometimes what I think is going to be an easy question is quite hard for a class, and that happened again. I thought this was going to be a giveaway, and actually it's the one that a lot of people choked on. Let's go over this for a second. So the problem was the algal condensation. I'm not sure why this caused problems, but I forget what the problem, I think, was this one, right? I had this and acetaldehyde. And the algal condensation product shown was this one. And I said, well, what other algal condensation products can you imagine? Now, notice that from these two reagents. The way you solve a problem like this is to think backwards, okay? So whenever we see an alpha-beta unsaturated carbonyl, what you want to do mentally is you want to break it into two pieces. So you look at this bond. This is something I did for you guys. So look at this bond. You think about breaking it, right? And so you think about this piece as having been a nucleophile, which shows CH2 minus, and the other piece, and I'm showing it now in a way that suggests the structure of the product, is the electrophile. And so if I'm going to get this kind of product, I have to get that sort of algal reaction, okay? So anytime you see an alpha-beta unsaturated carbonyl, we immediately mentally disconnect it into an enolate and an aldehyde, or an enolate and a ketone, or an enolate and an ester, or whatever the algal was. Algals are between ketones or aldehydes, but it's the same methodology. And so what you needed to figure out here is that, well, okay, so I could form an enolate here, that means deprotonation of that carbon atom, but hey, I could have deprotonated this position as well. And so if I deprotonate right there with base, then I will end up with a different enolate, but the same aldehyde. And so here I would form that as my product, as my algal product. Looking at it backwards, well, it looks the same way, right? I just break that bond. I see the aldehyde piece at the bottom. I see the ketone piece at the top. And then the third one would be the algal that you get from self-condensation of the acetaldehyde. So in other words, you break it apart this way, and you have 2 units of acetaldehyde, one acting as the nucleophile, one acting as the electrophile. Somehow this was a hard problem for a big portion of the class. And I don't really see why. I mean, it's very simple, I think. But somehow maybe it's because you don't understand the mechanism, or a lot of people do not understand the mechanism. If you know the mechanism, it's fairly straightforward. So anyway, by the way, I have posted the solutions to the exam. I did that on Saturday. I don't know if you got the email notification, possibly not, but they are on La Lima, and they have been for 2 days. So take a look at the exam solutions. They are posted. Okay, so, and by the way, when you get your exams back, if you have questions, of course, you can talk to me about it. So let's pick up where we left off with the amine chapter and see if we can make sense of some of the chemistry that we've learned in this chapter. The mechanisms and the reactions that amines undergo are a little bit different in carbonyls. However, the logic for many of them is pretty much the same. Now, there are a few reactions we're going to see in this chapter that don't really have a counterpart that is close to anything else we've seen, and I've alerted you to some of those. We're going to see some more. So one of the last things we talked about last time was the reduction of nitro compounds. And it turns out that, of course, nitro compounds are highly oxidized. The nitrogen and the nitro is oxidized, right? You have those two oxygen atoms. You reduce the nitro compound, then if you take it all the way down, if you reduce it as far as you can, you get the amine. And that's easy to do catalytically. You can also reduce nitro groups all the way down the amine using tin or iron. As you recall, low-valent metals are reducing agents. High-valent metals, like chromium-6, are oxidizing agents. That was another mistake that a lot of people made, and I'll digress for a minute. If you want to reduce a ketone, if you want to take a ketone to alcohol, you need a reducing agent, right? That means you're not going to do that with chromium-6. Chromium-6 does the opposite reaction. It takes an alcohol and takes it to a ketone. That's an oxidant. So you need a reducing agent to go from ketone to alcohol. One way to think about that, by the way, is as follows. If you are reducing a ketone to an alcohol, just think about what has to happen. You have to take this ketone and add the elements of hydrogen across that double bond. That's a reduction, pretty clearly. Anytime you're adding hydrogen to something, it represents a reduction. And so you're not going to do this with chromium plus 6. Where's the hydrogen coming from, for one thing? And so you need a reducing agent, typically sodium borohydride, but you recall that these conditions will also reduce carbonyls to alcohols. And so, typically other things happen too, so this is not the preferred way for reducing a ketone. But it is a good way to reduce a nitro group to the amine. Notice that the carbon-bromine bond does not undergo reduction. Now that's important because these conditions, just so you know, will very often cleave that carbon-halogen bond to give HBr and the proton there. So that's one of the reasons it's nice to have complementary ways to do the same thing. You can say that, well, you know, if we can do it catalytically, who cares whether you can go with tin and iron? The reason you do care is because it gives you control. In one case, you can stop before you get before this undergoes reduction. In the other case, you have ways of reducing the nitro to the amine without having to use strong acids. So that's why it's useful to have multiple ways to take a nitro from amine. Now, it turns out that LAH does something kind of strange, and we don't need to go through the mechanism, but it will convert aniline to an azo compound, so azobenzene. Now, the very last thing we talked about was a cross-coupling reaction, this Buchwald-Hartwig emanations. And this is new. I mean, this is, you know, in the last 10 years. And it allows you a very nice way to get primarily aromatic amines. So the way you do this is under the same kinds of conditions that you remember for Suzuki and Stille and the other cross-coupling reactions we talked about. You have palladium-0 catalyst. You have some kind of a ligand. We're going to talk about that. And then the amine. And so what this is not doing, okay, what this reaction is not doing, it's not doing a nucleophilic aromatic substitution. The reason you know that is because in order to get a nucleophilic aromatic substitution, you need a truly electron-poor aromatic ring. The aromatic ring has to be substituted with a couple of nitro groups typically, or something electron withdrawing to stabilize that initial charged intermediate that you get. Here you don't have that. Here you just have methyls, an electron-rich ring. And so the mechanism here has to be a little bit different. The ligands, as it turns out, are important. I don't want to make too much of this, but these are the kinds of ligands that are used, the phosphines, that have two alkyl groups and an aryl group. Now, these are electron-rich phosphines. Why electron-rich? Well, because the alkyls are more electron-donating than the aryls. The aryls have an sp2 hybridized carbon atom. Remember, those are electronegative compared to sp3. Also, especially in this case, 2-butyl groups of this orthophenyl benzophenyl, so orthophenyl-phenyl. This is extremely hindered, right? And so those two features turn out to be key to enabling this reaction. Try to do this kind of Hartwig-Buchwald amination and use triphenylphosphine. They don't work. And so this highlights something that I mentioned to you way back when we talked about in chapter 18, organometallic chemistry, transition metal organometallic chemistry, that area is particularly rich, and that you can really modulate reactivity to a great degree by choice of ligands. So same metal, but different ligand, different reactivity. Now, the mechanism is pretty much the same one that we've seen before, with one little twist. Remember that that these ligands are very hindered. Okay, there's two butyl groups. So in general, it's going to be difficult to get two of those phosphines attached to one palladium. And so that ensures that the palladium is not 18 electron, and that ensures reactivity. So you have two ligands, you dissociate one, then as soon as you do the oxidative addition to the aryl halide, you already have three substituents of this palladium. Very hard to get another big ligand here. So this is now a 14 electron complex, and it is reactive. It does the ligand substitution, and then also the reductive elimination. The reductive elimination, by the way, is driven by release of steric compression. In other words, having a large ligand, large bulky ligand on palladium, if you like to think about it, kind of pushes the other two, these two, to undergo that reductive elimination. And so the design of these ligands, you see, is critical to the success of the reaction. And so this chemistry works rather well. Now, one thing you have to recognize is this, that we've picked a secondary amine here, and I did that for a reason. The reason is that in the product, I have no NH group, right? Now, if I have an NH group in the product, then you can imagine that that product can enter the catalytic cycle a second time. And so if we use a primary amine, then you can add actually two aryl groups to that amine. Why? Well, because the product still has an NH. The product can still do a ligand exchange on the palladium, and you can still get the reductive elimination. Now, the way to get around that, the way you avoid getting a double addition, is you just use an excess of the amine. And if the amine is expensive, you recover it at the end of the reaction. So it's not, it's not maybe the ideal way of doing it, but it works. So this is the new way to form aryl amines from aryl halides. It turns out that the chemistry also works with triflates. Remember trifluoromethane sulfonates? We first encountered trifluoromethane sulfonates as derivatives of alcohols so that we could do SN2 reactions. And so remember that you can convert an alcohol into a good leaving group by making a sulfonate ester. You can make a mesylate, methane sulfonate, make a tosylate, olivine sulfonate, or you can make a triflate, trifluoromethane sulfonate. Now the triflate, all those three sulfonates, is going to be the best leaving group because this is the weakest base. Triflates work really well for this chemistry and for a lot of other cross-coupling reactions, by the way. So they stand in for halides. So for most of these reactions, a halide, bromide iodide triflate can be used. And in this case, for a Buchwald-Hartwig reaction, these work really well. So the mechanism is the same. Instead of getting oxidative addition to an aryl bromine bond or an aryl iodine bond or whatever, you get oxidative addition to an arrow oxygen bond, where the oxygen is part of a triplet. And so as long as this is a electron withdrawing group, you can do this chemistry. So this is another way to form these carbon-nitrogen bonds. In this case, not starting from a halide, but starting from an alcohol. And so now you can see that you have under your belt a lot of methodology that you understand that will allow you to build complexity in an aromatic ring in a systematic way, especially now that you've talked about, that you've learned diazonium ion chemistry. So this is a very powerful set of tools that allows you to generate pretty much any kind of aromatic substitution pattern that you want. Okay, so let's shift gears a little bit and talk about Curtius and Hoffman rearrangements. And by the way, I don't want you guys to obsess about the names, right? I mean, the names are not what's important. Remember them, that's great. Don't, no problem. What I do expect you to remember are the mechanisms, okay? So don't try to memorize the names, but please pay attention to the mechanisms. Now, once you see these mechanisms, they're going to make a lot of sense. Here's how it works. Start out with an acyl azide. Okay, now how do you make an acyl azide? Well, okay. So let's think back a little bit. When we talked about stability series of carbonyls, right? We said that nitriles and amides were all the way to the non-reactive side. What was the most reactive carbonyl derivative that we had? Yeah, an acid chloride. So the way you make an acyl azide is you start with an acyl chloride and you use sodium azide as the nucleophile. And so you get a tetrahedral intermediate where the azide acts as the nucleophile. And now the chloride, which is a weaker base than N3-, departs, and you end up with acyl azide. And I'm going to show the acyl azide in one of its resonance structures. Okay, so it has others, but I'm going to show that one. Okay? Now, the reason I show that is because I look at this and I have an N2 group all the way to the right, which looks like the world's best leading group. And so what this suggests is that these acyl azides should be pretty reactive, right? Because, hey, I have this nitrogen, this can depart as N2, a neutral molecule, the world's weakest base, the world's best leading group. Something is going to happen to this if I heat it up. And so if you heat up an acyl azide, something does happen. It turns into an isocyanate. And so I want you to kind of figure out what's happened here. This R group, which used to be bonded to the carbonyl, ends up bonded to the nitrogen. I have an R nitrogen bond. The carbonyl is still there, and I've lost N2. So, gee, how did that happen? Well, let's take a look and see. So here's how you imagine this happening. You take this electron pair, the red one, and you do a concerted reaction like so. Okay? So from the right, you can see that nitrogen is now neutral, so you've lost the neutral N2. You've taken an electron pair away from this carbon, so if I just draw the resonance structure that this leads to. I'm going to draw it, by the way, just the way the starting material looks so you can see what's happening. Okay, there's the migrating electron pair. There's the R group, and here's N2. Now, this nitrogen gained an electron pair, lost an electron pair, so it's still negatively charged. This carbon would have to be positively charged. And this is an unstable resonance structure of, you guessed it, that. Okay? So you form, I mean, this isn't, you don't end up with this charged species, you end up with that because the electrons, because it's a concerted process. And so you form the isocyanate just by migration of this R group to the nitrogen atom with loss of N2. you need to draw this out, as usual, for all the mechanisms. You need to confront a blank piece of paper and draw it out until it's obvious to you that you know how it works. Now, isocyanates are reactive, as you can imagine. This carbonyl looks as if it should be very reactive, because why? Well, because that carbon atom that I'm pointing at is hybridized. What is the hybridization of that carbon atom? SP, correct. It's SP hybridized because bonded to only two things, correct. And so it reacts with water to form a carbamic acid. Carbamic acids are not stable. So carbamic acids spontaneously lose CO2. And so what you end up with in the end is the amine. Now, carbamate esters, on the other hand, are very stable. And so I'm trying to think of the structure. I can't remember the structure. But if I have a carbamate ester like so, these are very stable. These are completely stable. But carbamic acids, where that's an OH, those lose CO2. What are carbamates used for? Does anybody know? Anybody heard of carbofuran? That's the structure I was trying to remember. Carbofuran. It was banned in Hawaii some years ago. It's an insecticide. And the reason that it was banned is because it's got very high mammalian toxicity, to the point that you needed a license to use it. They used to use it for bananas to kill corn borers, these little insects that bore up through the banana plant. So before you planted a banana tree, you dug a hole, poured some carbofuran pellets in there, and then filled the hole. The problem is that if you absorb enough carbofuran yourself, you're toast. And so those insecticides are probably best not used. Not that there's an ideal solution. The neonicotinoids that are being used now are killing off the honeybees. So anyway, so acylazid rearranges with heat to give an isocyanate. Isocyanate adds water and get a carbamic acid, and then this loses CO2 to give you the amine. This loss of CO2 takes place either under base or acid catalysis. So, what does the acylazid, what does that Curtius rearrangement do? Well, it splits out one carbon atom, right? So I start out with a carboxylic acid and end up with an amine that's got one carbon atom less. So let's take a look at it. Let's just say that I start out with carboxylic acid. Now I know that I can go from the acid chloride, to the acylazid. So, and then I'm going to end up at the end, after the Curtius rearrangement, the amine, which means that carbon atom is now lost as CO2. So in one sense, what you're doing is the reverse of a one-carbon homologation. Remember one-carbon homologations? In fact, there's a one-carbon homologation on the exam. That was the synthesis problem. And so a one-carbon homologation means I start out typically with alkyl halide, and then I end up with an alkyl halide that's got one more CH2. Here, I start out with a compound that has one extra carbon atom, and I end up chopping off the carbon atom and ending up with the amine. So I just mentioned that to, so that you see kind of a continuity here. So in net, this carbon atom is lost as CO2 and you end up with the amine. Now the mechanism is the one that I've shown. It's a concerted reaction where all of these electrons move at the same time, to rearrange at the same time to give you the carbamate and nitrogen. This last electron, this arrow is the one I didn't show. I showed just the two arrows, so it would be a little bit easier for you. But of course, that this process is concerted, and you end up in one step going from here to the usual carbamate. So isocyanates, by the way, are isolable. So you can isolate these. They, as long as you keep them away from nucleophiles, away from water and amines and alcohols, they're perfectly isolable. On the other hand, if you you allow them to react with nucleophiles, like amines, you end up with ureas. If you allow them to react with alcohols, you end up with carbamates. And so if I do a Curtius rearrangement in the presence of, say, methanol, then I'm going to end up with a methyl carbamate. Now, does this look really that much different from the ester chemistry that we talked about? Well, a little bit different, because in the ester, the carbonyl, or the acid chloride, the carbonyl group was sp2 hybridized. Here, the reactive electrophilic carbon atom is sp hybridized. But, you know, it's more or less the same kind of chemistry. So these two reactions should come as no surprise if you understood the ester chemistry. Okay, now the preparation of acyl azids is the one that I showed. You start from the acid chloride all the way at the reactive scale, end of the reactivity scale. You use sodium azide as your nucleophile, and you end up with the acyl azide. You get the tetrahedral intermediate, that collapses, that gives you the acyl azide. The acyl azide is stable at room temperature. If you heat it up, then of course you get the Curtius rearrangement. Now, one thing you need to recognize, azids in general are going to be thermally unstable. And so if I prepare a molecule that's got, 1, 2, 3 azido functions in it, I probably want to work with that material behind a shield because it's likely to be energetic. Okay, so azids are reactive functional groups. Now, it turns out there's another way to make an acyl azide that makes use of again, chemistry that we talked about in this chapter. Okay, so here's the way you want to think about this. Let's think of an amine group here, just an amino group, right? So a primary amide. And let's think about just a primary amine. PRs will have to be the same. Do we know a way to go from here to there? Do I know a way to go from an amine to a diazonium salt? And how do I do that? How do I convert an amine to a diazonium salt? Use sodium nitrite and acid. Okay? So that's how you do it. Now, this amine is not going to give me an acyl azide. So this is not quite what I want. So what I want really is this kind of an amine. And by this amine, I can convert that into a diazonium salt pretty much the same way that you saw for this, and end up with an acyl azide. So let's take a look and see how that works. So remember this stuff. This stuff is hydrazine. It's a strong reducing agent, inter alia. Where do we see hydrazine? We've seen this stuff before as a reducing agent. For what kind of reduction? Huh? Where did we see hydrazine? Yeah, we saw it. Yeah, Wolff-Kishner reduction, remember? So if you want to take an aldehyde or a ketone down to methylene, then you treat it with hydrazine and strong base. That was the Wolff-Kishner. So if I have a ketone like this, I treat it with hydrazine. That's the reducing agent. Hydroxide, holy heck out of it. And what I end up with is not the alcohol, but the methylene. And so this was known as the Wolff-Kishner reduction. Okay, so I'm taking it all the way down. This forms a hydrazone and so on. This is a good nucleophile, and so it should come as no surprise that we'll do a displacement of an ethoxy group in an ester, just the way any amine will. Now this is a special kind of an amide. It's called a hydrazide, because I started with hydrazine, so the amide is called a hydrazide. Okay, no big deal there. Now, if I do the same kind of diazonium reaction that you saw before, I'll end up with an acyl-azide. I just diazotize that nitrogen atom, and so the way you think about this is just the way I said. I start with an amine, I do a diazotization. I start with an amine, I do a diazotization. So there's the nitrogen atom that came from the sodium nitrite. And so you don't, by the way, this is going to be extremely acidic, and that's why it's lost. This is acidic because you have a positively charged nitrogen here and a partial positive charge there. So that proton is easily lost. You end up with the acyl-azide. But there are two ways to make the acyl-azide. Go from the acid chloride, just using sodium azide, or start with the acyl hydrazide, do the diazotization. They both get you there. Mechanisms, of course, are different. Okay? Now, the Curtius rearrangement is not the only rearrangement that gives you a isocyanate. And so there's this Hoffman rearrangement business that we talked about. And so let's take a look at that. So the net effect is the same. I start out with an amide, and then I end up losing CO2, and I end up with an amine that's got one carbon atom less. But the conditions are different. The mechanism, of course, is quite different. So I start out with primary amide, treat it with bromine and base, end up with the amine. This carbon ends up as CO2. So how does this happen? Well, okay, so sodium hydroxide and this primary amide will lead to a proton transfer reaction. And so you can think of this as being almost like an enolate, right? I mean, it looks sort of like an enolate, but instead of having a carbon there, I've got a nitrogen. But it looks more or less the same as enolate chemistry. Pull off an alpha proton, end up with an alpha negative charge that's delocalized into the carbonyl. Now, this is a nitrogen nucleophile. Just the way an enolate was a carbon nucleophile, this is a nitrogen nucleophile. So if I add bromine to that, I will get the expected N-bromination. So if it was carbon, the bromination would take place on carbon. But because I have, let's just draw this resonance structure. If I have bromine, which is a good electrophile, then I can imagine that reaction taking place to give me a nitrogen bromine bond and Br minus. So that's what happens here. End up with a nitrogen bromine bond, there's Br minus. Now, just as we saw for the haloform reaction, once you brominate on that nitrogen, the next proton removal is going to be quite a bit faster than the first. And so you're going to form this intermediate. Now, take a look at that and compare it with what we saw for the Curtius rearrangement. It's more or less the same, right? For the Curtius rearrangement, so take a look at that. And now let's take a look at the Curtius rearrangement over here. I have a negatively charged nitrogen atom and a leaving group there. And so the same kind of rearrangement that took place with the Curtius rearrangement takes place here. It's just the leaving group's different. Instead of N2, I've got bromide as the leaving group. And so, you know, no big surprise, it works the same way. And so this gives you the isocyanate, just as we saw before. Now, there's one difference. And the difference here is that the Hoffman rearrangement takes place in the presence of hydroxide. And this, as you know, is reactive to hydroxide. And so you really can't isolate the isocyanate from the Hoffman reaction because hydroxide intercepts that really fast. You lose CO2 and you end up with the amine all in one step. And so if that's not an issue, then either reaction can suffice. If you want to isolate the isocyanate, then of course you have to go via the Zid and do the courteous rearrangement. But the key is this concerted process that allows migration in the R group to take place to the nitrogen with loss of the leaving group. Now, I hasten to point out that since both reactions, both the Hoffman and the courteous, are concerted, that means that stereochemistry of that R group is not lost. So if that R group is chiral, then you end up with a single enantiomer of the product. So whether you do a courteous or a Hoffman, if you have a single enantiomer here, then you end up with a single enantiomer of the amine. And so the only reason that happens is because you don't end up with an intermediate radical carbanion or carbocation, which would be planar and which would allow stereochemistry to scramble. And so this is pretty good evidence of the concertedness of the reaction. That's a point that I brought up before. When I say, well, this reaction is concerted, really, how do you know? Nobody can isolate a transition state, and so if you don't really know the transition state, then you really can't be 100% sure of the mechanism. And so the way you figure out what happens with the mechanism is you infer the mechanism from things like this, that the reaction is stereospecific and preserves stereochemistry. Okay, so the courteous and the Hoffman reaction are a little bit different from things we've seen before. We've seen molecular rearrangements taking place primarily with carbocations. This is a little bit different. It shares some features of the rearrangements that we've seen before, namely a group migrates with its electron pair. And so if you think back to what we learned about carbocation rearrangements, there is some similarity here, but yes, this is new. Something else that's new here is going to be the Staudinger reaction. And the Staudinger is it's useful for a number of things. There's a problem at the end of the chapter that shows you one of the applications of Staudinger. But this will convert an azide to an amine. So you can think, well, what's the big deal? I can take an azide and actually I can reduce it to the amine using catalytic hydrogenation too. I don't need to use a Staudinger. But the Staudinger works really well. So look what happens. I take an alkyl halide, do an SN2 reaction with the azide, normal chemistry. Then I treat this with triphenylphosphine. Any kind of trialkyl or triaryl will work. And you end up getting nitrogen. So this spits out nitrogen and gives you this species. What does this look like? Have we ever seen anything like that? Yeah, it looks like a Wittig reaction. In fact, it's sort of a nitrogen analog of Wittig. And so this looks like the kind of illet that we saw when we were doing Wittig reaction, except there we had carbon. As it turns out, this will react with aldehydes, okay, but we don't need to talk about that. If you hydrolyze it, you end up with the triphenylphosphine oxide and the amine. So it takes the azide to the amine. The mechanism here is one I can talk to you about if you're curious. There's some uncertainty about the mechanism, but it involves the formation of a trier bond of the phosphorus to the end nitrogen. Okay, so Staudinger is something new. We haven't seen that before. Now, amines play a center stage role in biology, and a lot of them appear as plant products as well. So a lot of plants, familiar ones and unfamiliar ones, produce heterocyclic amines. And so one term that you're going to encounter is alkaloid. And so when you hear alkaloid, of course, the first thing you think of is alkali. And in fact, that's where the name comes from. So alkaloids were named as plant-derived alkalis being bases. And so these are some of the fairly common ones that you may have heard of. So nicotine is an alkaloid. We've seen this before. It has a pyridine and a pyrrolidine, so this is nicotine. Arecoline is simple compound, doesn't have any stereochemistry. Notice this has a single stereo center. Nicotine is found, of course, in tobacco, where it serves, by the way, as an insecticide. In the good old days, nicotine was used as an insecticide. And arecoline, where do you find arecoline? Do you have anybody from, who grew up in the Philippines? How about Micronesia? No. This is betel nut, okay? So when you chew betel nut, arecoline is what gives you the buzz. You've heard of areca palms? That's where the name comes from. Cocaine comes from the leaves of a Andean shrub. We all know about that. Morphine is found in poppies and is still the primary medicine used against severe pain, in spite of its toxicity and the other problems associated with it. It's still very, very useful. Mescaline, where does that come from? You know, I think so the drug preferences of the youth must have changed quite a lot from my time. This is the active principle that you find in mezcal buttons. Those are hallucinogenic cacti that grow in the Sonoran Desert. Those cacti were used and are used as part of a religious ritual by some of the Native Americans. Okay, so this doesn't have a heterocyclic nitrogen atom, but it fits a pattern that you will see. Then lysergic acid, the ethyl ester of this is LSD. Now, what I want to draw your attention to is the fact that these three compounds have a shared functional feature. And that turns out to be important in their physiological activity. And now I guess I don't want to draw it out, but let me just show it to you. It's easiest to see here. All of these are phenethylamines. So I have an ethylamine, 2 carbons, amine, with an aryl group. So if you look in here, there's the aryl group. Carbon atom 1 is here. Carbon atom 2 is there, and there's the nitrogen. So aryl group, carbon atom 1, carbon atom 2, nitrogen. There it is. In lysergic acid, aryl group, carbon atom 1, carbon atom 2, nitrogen. And so the conclusion, and there are many others that fit the same pattern. If you look at human neurotransmitters, adrenaline and dopamine have that same function, right? They're phenethylamines. Here, of course, with a methyl group and a hydroxy and so on. Methamphetamine, not a neurotransmitter, also has that feature. And so the pattern is a fairly clear one, that when you have that phenethylamino function, that fits into a cell receptor or family of cell receptors, and the physiological activity is related to that particular structure. So that wraps up what I wanted to say about this chapter. This is chapter 23. In the time we have remaining, let's go through and kind of review some of the stuff. This was a chapter on amines, so we talked about a fair amount of amine chemistry, although I would like to think that most of the mechanisms followed a pattern that you recognize. And so let's take a look here first of all. Now, amines come in different substitution patterns, the simplest one being ammonia, and then primary, secondary, tertiary, and then ammonium ion, where you have all the valences saturated. Tertiary amines, secondary amines are not chiral. And they're not chiral for a strange reason. Remember that you get that very fast at room temperature fast amine inversion process. So even if you were to make a chiral secondary or tertiary amine, that would racemize in less time than it takes to talk about it. And so that turns out to be something that is unique to amines. So the amine inversion mechanism, remember, is the one that looks sort of like an SN2 reaction, or pardon me, it looks, yeah, SN2 reaction. You can imagine for an SN2 reaction, you have a nucleophile approaching carbon, flatten it out, and then you have the inversion. Here, it's the sp3 hybridized orbital that rehybridizes to 2p and then back to sp3, going from tetrahedral to planar to inverted tetrahedral. And so this process taking place reversibly ensures that you don't get optical activity from a secondary or from a tertiary amine. Spectroscopy, I don't want to go through this in any great detail. Just remember that what IR is good for is determining the presence of functional groups. And so the infrared spectrum is almost always going to be the best way to determine whether you have any specific functional group. In this case, an NH shows up as a double peak at this frequency. Of course, if it's a tertiary amine, you don't have that. And CN doesn't work very well. CN is not a diagnostic peak in the IR. Now, the importance of amines, or the important features of amines are related to the presence of the non-bonding electron pair of nitrogen. That non-bonding electron pair can react with protons, rendering the amine basic. So it acts as a Bronsted base. It acts as a Lewis base too. And it also acts as a nucleophile. And so there are two kinds of reactivity that you get from that non-bonding electron pair. Anything that stabilizes, any feature that stabilizes the amine, of course, will decrease basicity. If you stabilize the ammonium, you increase it. We talked about hydrogen bonding. I don't want to go through that again. But certainly, you need to be aware of the fact that any feature that destabilizes the ammonium ion, like placing an electron withdrawing group here, is going to make that a stronger acid. And so you can see that. Also, you need to recognize that there's a big difference in acidity between aniline, anilinium ions and non-aromatic ammonium ions. You know, this is a very large difference. It's related to the fact that the amine here is stabilized by overlap with the electron pair into the aromatic ring. And so that causes about a million-fold increase in acidity for the aniline. We talked about phase transfer catalysis. And phase transfer catalysis, remember, made use of either ammonium ions or sometimes called phosphonium ions. And the way this worked was that you had a water-soluble, organic insoluble ion, cyanide, that is then dragged into the organic phase by association with a lipophilic ammonium species. So sodium is not lipophilic. Sodium cyanide doesn't dissolve in organic solvents. But the ammonium cyanide that I've shown here does dissolve in organic solvents because this is soluble. Because this is soluble and because it drags with it a negatively charged cyanide, then the cyanide becomes soluble in the organic solvent. And so that allows you to do chemistry in the organic phase that normally you can't do. So if I just take, for example, sodium cyanide, an alkyl halide, and throw them into an organic solvent, nothing's going to happen because the sodium cyanide won't dissolve. On the other hand, if I put some phase transfer catalyst in there, then yes, I will get a very fast reaction. And the reaction is fast for another reason. It's fast because in the organic solvent, the cyanide is not solvated by water. So it's sort of like a naked anion. So you don't have a high activation barrier to overcome by pushing away the solvents that would surround, solvent molecules that would surround that. Okay, now the direct alkylation of amines is not going to work. And this is something that you need to always be aware of, that because of this dual nature, because the amines are both nucleophilic and basic, if I try to stop after a single alkylation, that reaction will never work. It won't work because I'll get proton transfer, generating secondary nucleophile. That will react with the electrophile and so on, until I end up with ammonium ion and perhaps a mixture of mono and di and trialkylated amines. And so to overcome that, we've had to figure out a few little tricks, like the Gabriel synthesis that use phthalimid and reductive aminations for getting secondary and tertiary amines. And we've reached the end of our period, so I will see you all on